Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Let's start our class today by reciting prayers and blessing upon Nabi Muhammad sallallahu alaihi wasallam. Bismillahirrahmanirrahim. Rabbi zidni ilman warzuqni fahman. Allahumma salli ala sayyidina Muhammad salatan taj'aluna biha min ahli ilmi zahiran wa batinan wa tahsyuruna bi ibadikas salihin fi dunyana wa akhrana wa ala alihi wa sahbihi wa barik wa sallim. Okay, we will continue our lecture on chapter 2. So, there are many types of lighting circuit that can be designed in our building. For example, we have a single light point controlled by a one-way switch. So, this is the circuit of the lighting. So, we have one light point here and then we have also one-way switch here. So, to turn on the light, we need to turn on the switch, so that when the switch is turned on, light will be on. We also have two light points controlled by a one-way switch. So this is the circuit. So we have two light point here, L1, and then we have L2, which is controlled by one switch here. So one-way switch. So if we turn on the switch, so both lamp will be turned on. Okay, we also have a lighting circuit that consists of two light points controlled separately by two one-way switches. Okay, this is the circuit. We can see that we have two light points, L1 and also we have L2, and then controlled by two one-way switches, S1 and also S2. Okay, in case we want to switch on the L2, we need to switch on the S2. And then if we want to turn on only L1, so we need to switch the S1. So each switches control one. Another example of lighting circuit are single light point controlled by a two-way switch. So this is the circuit. So we have one lighting point here and then we have two-way switches. Usually this kind of lighting circuit used at the staircase. So for example, we have one light bulb here and then we use two-way switch. So before we go to the first floor, at the ground floor we turn on the light bulb, and then when we arrive at the first floor, we turn off the light bulb using the second switch. Okay, we also have three light points controlled by two-way switches and intermediate switch. So we have three light points here, we have two-way switches, and in the middle we have the intermediate switch. So usually the this kind of lighting circuit are being applied at the staircase, which the two-way switch we located at the ground floor and the first floor, and then the intermediate switch is between the floor. So okay, this is the connection of the intermediate switch. Other than that, we also have a single fluorescent light point controlled by a one-way switch. Okay, this is the example of the circuit. In this circuit, we have a switch, one-way switch. We have a capacitor. We have also choke. We have a filament. We have a tube, and also we have a starter. Okay, for your homework, so you need to watch this video at this link and explain how the operation of this kind of circuit. Now we move to the examples of socket outlet schematic wiring. For a single socket, we can see that this is the connection of the single socket. This is earth wire, this is the neutral wire, and then this is the live wire, represented as a supply. And then the socket outlet can be in a radial connections. So radial connection is connect to SSO to a supply. So this is the example of radial connection. And then for ring circuit connection, we have more than 3 SSO connected to a supply. So many SSO connected to one supply called as a ring circuit connection. Okay, this is the final circuit for 13M socket outlet. So we have two types of circuit, ring and radial. So for the ring type of circuit, we need to use MCB 30 or 32M. For the minimum size of copper conductor is 4 mm squared. And then for the maximum floor area, 100 meters squared. And then for a radial type of circuit, we need to observe the maximum floor area. If the maximum floor area is 50 meters squared, we need to use the minimum size of copper conductor is 4 with the MCB rating 30 or 32M. And then if the floor area is 20 meters squared, we need to use the minimum size of copper conductor 2.5 mm with the rating of the MCB is 20M. And then this is the minimum cross-sectional area rating of wiring conductors. So different size of conductors, cross-sectional area, we will have different application with a similar material. This you can read. Okay, now we move to some electrical accessories. Okay, for the first accessories, we have a lamp. So for fluorescent lamp using magnetic ballast which watt loss not exceeding 6 watts shall be equipped with dry paper type capacitor. And then for the fluorescent lamp using electronic ballast, this is the recent technology, or high frequency electronic ballast doesn't need any capacitors. And then we have the outdoor domestic lamp, which is the installation shall use weatherproof and waterproof lamps. And then we also have a submerged light, which is the installation usually in the swimming pools, fountains, etc., which shall have waterproof lamps with a voltage not exceeding 12 volt AC. Another electrical accessories, we have electric water heaters, which is divided into two types. The first type is the storage water heaters, also known as storage tank type, shall be installed with an isolator and its own residual current device. And also the second type is instantaneous water heaters, shall be equipped with a 2-pole control switch and its own residual current device. So water heaters exceeding 3 kilowatt shall be permanently connected to a 20 amp or 30 amp rated circuit breaker or fuse with an isolator switch and residual current device. And then we also have electric motors, which usually connected to the fence gate, air conditioners, fountains, swimming pools, fish pond, water pumps exceeding 373 watt but not exceeding 2238 watt shall be connected permanently to a 20 amp or 30 amp rated circuit breaker or fuse together with an isolator, motor starter and 15 amp socket outlet. The motor starter shall be of direct online type with the appliance together with the contactor, overload relay and on-off control. The circuit breaker or fuse which control the motor circuit shall be capable of withstanding the starting current of the motor. Other electrical accessories are including the electric bells. So, the circuit of electric bells shall have a push button switch and a AC-DC transformer. Other than that, we have a ceiling fans. The ceiling fans shall conform to clause 21.101 of the MS 1219/2002 standard with regards to tests on the suspension system of the ceiling fans. Okay, for the industrial electrical system design, we have 5 design components. We have a non-motor circuit, we have a motor circuit, we have a circuit serving several motors, we have a panel box and switch box, and finally we have a transformer. Okay, for non-motor loads, the MCCBs or fuses are not allowed to carry 100% rated current on a continuous basis. It is normally limited to 80% of the circuit breaker rating. So, for overcurrent, usually equal to 1.25 times the load ampere. And then, for the wire, is equal to 1.25 times the load ampere. Okay, for design MCB or MCCB, which is less than RCCB or RCD sensitivity, lighting circuit is 100 milliamp, power circuit is 30 milliamp. For example, a 240 circuit carries a load of 1200 VA. What is the correct MCB size? So we can use this equation, I equal to kVA divided by kV. So we have 5 amp here. So for the overcurrent, we use the equation 1.25 times the load ampere 5 amp. We have 6.25 ampere. Since we don't have this kind of MCB, so we take the MCB 10 amp. And then for motor circuit, we have a motor inrush current during start up, usually 5 to 7 FLA. So inrush current is the starting current. Meanwhile, the FLA is a full load ampere. Usually this full load ampere is represented in a table. We will see in the next slide. So, in the motor circuit, we have 2 protective devices, which is MCCB and also time delay fuse. So, the equation for MCCB for overcurrent, we have 1.75 times the FLA, full load ampere. While for the wire is equal to 1.25 times the FLA. Whereby for the time delay fuse, the equation is for overcurrent and also wired is equal to 1.25 times the full load ampere. So this is the note. OC for overcurrent, wire is for cable. Okay, this is the example of FLA for one-phase AC motors. So we move to the example. So you need to design a circuit to serve a 10 horsepower 240 volt single phase AC motor. The overcurrent device is a MCB. So the solution from the previous table, FLA table, we know that for the 10 horsepower 240 volt, we have a FLA at 50 amp here. So this is horsepower, and then this is the range of volt. So usually 230 to the 240. So have 50 FLA. So we, from the previous slide, we know that for MCCB overcurrent device, we need to use this kind of equation. So that the equation is overcurrent device equal to 1.75 times 50 FLA we got from the table, so equal to 75.5 ampere. So we don't have this kind of MCCB, so we use the rated 100 amp with one pole. So for wire or cable, we equal to 1.25 times 50 ampere equal to 62.5 ampere. Okay. We also have a circuit serving several motors. So for MCCB overcurrent, the equation is equal to 1.75 times full load ampere for largest motor plus sum of FLA for smaller motor. And then for wire or cable is equal to 1.25 times full load ampere for largest motor plus sum of FLA for smaller motors. For time delay fuse, we have a overcurrent circuit equal to 1.25 times full load ampere for largest motor and sum of the FLA for smaller motor. For wire or cable equal to 1.25 times full load ampere for largest motor plus sum of FLA for smaller motors. Okay, we have an example here. An air conditioning unit has two motors, a 5 horsepower compressor and a 1 horsepower condensing fan. Both motors are rated at 240 volt single phase. Design a circuit for this unit using a MCB as the overcurrent device. Okay, so from the FLA table, we need to find the FLA for 5 horsepower and also 1 horsepower. So for FLA for 5 horsepower is equal to 28, and then for 1 horsepower equal to 8 amp. And then we used since we need to design a MCB, so we use this kind of equation. So for overcurrent device equal to 1.75 times the FLA of largest motor. So between 28 and 8, 28 ampere is largest motor, so we times 8 plus the smaller motors. So the smaller is 8, so equal to 57 amp. So we use the 60 amp one pole MCB. And then for wire is equal to 1.25 times the largest motor FLA 28 amp plus the smaller motor 8. So we have 43 amp. Okay, now we move to the transformer. So, transformer must have overcurrent device protection on both sides, which is primary sides and also secondary sides. So, this is the equation for overcurrent device for both sides. So, we can see that both sides have a similar equation, which is the overcurrent device for primary and secondary is equal to 1.25 times the FLA, full load ampere. And then the FLA is determined from the transformer's rated kVA and voltage, not the load current. So we will see this. Okay, now we have an example on transformer. So a 50 kVA step down transformer with a 3.3 kV 3-phase primary and 415 secondary is selected to serve a lighting panel. Select the correct overcurrent device for this transformer. So to understand this question, we need to understand some point. Such as we know that from the question 50 kVA is the S value, and then 3.3 kV is the voltage primary, and then we have 415 is the secondary voltage. And then so we draw the circuit. We know that from the supply go to the MCB and then go to the transformer. So this is the primary voltage, and then step down to the secondary voltage 415 volt, go to the MCB and go to the load. And then we rearrange by using some equation here. So we know that S is equal to 3I phase times V phase, where V phase equal to V line to line divide by Z3, and then rearrange it, and then finally we know that FLA is the kVA divided by Z3 times kV. Okay, from the previous discussion, we know that I is equal to kVA divided by Z3 times kV. So we can calculate the current for primary and secondary side. So we have 8.75 ampere I primary, and then we have 69.56 ampere for secondary. So by using the equation, so we got the overcurrent protection device for primary side is 1.25 times the FLA equal to 10.98 ampere. So approximately we use the 15 amp 3-pole MCCB. And then for secondary, we have 1.25 times 69.56 amp got equal to 86.95 ampere. We use approximately 19 amp rated. Okay, now we move to the panel boards and switch boards. So let's say we have lighting, air conditioning, water heating, ceiling fan, refrigerator, lift, and booster pump. So the demand factor of these appliances depends on the usage and lifestyle. So let's say for lighting, the demand factor we choose 0.8. So the air conditioning 0.5, water heating 0.3, ceiling fan 0.8, refrigerator 1, lift and booster pump is 0.5. Okay, let's say we have an apartment consists of fluorescent lamp with 40 watts, ceiling fans with 60 watts, 13 amp socket outlets with 250 watts, 1 number water heater with 3 kilowatts, 1 horsepower air conditioner. And then we need to determine the total maximum demand, maximum current, size of MCB, size of RCD, and finally we need to draw the electrical wiring schematic diagram. Let's say we are given architect layout like this. So from this layout, we need to determine the number of fluorescent lamps, ceiling fans, socket outlets, and etc. So from this layout, we know that we have 3 bedrooms, and then we have 1 living room. This is the bathroom and toilet, and then this is the kitchen. So from this layout, we need to count how many fluorescent lamp we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 fluorescent lamp with 40 watt. And then we need to count how many ceiling fans. So 1, 2, 3, and 4. So we have ceiling fans with 60 watt 4 units. And finally, we need to count how many 13 amp socket outlets. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 13 amp socket outlets, 10 units. Okay, we have 1 number of watt heater and also 1 number of horsepower. And then the solution, we need to draw the load calculation. So we know that the quantity of the lighting, ceiling fans and 3M SSO we got from the layout just now, 12, 4 and 10, 1 and 1. And then the estimated power given in this question, we know that. And finally we can calculate the total connected load. So we know that total connected load is equal to quantity times estimated power. So we know lah. Okay. And then the demand factor is depends on our usage and lifestyle. So we choose our assumption. And finally we can get the maximum demand by using total connected load times the demand factor. We have the maximum demand. And then from that we calculate the total maximum demand, and then we know the coincident factor from ESA, and we can calculate also the maximum demand. Okay, now we move to the solution. So the question was asking what is the total maximum demand. So the total maximum demand is the sum of the total maximum demand at each appliances. So from the table we got 3101 watts. And then the maximum demand also, we know that total maximum demand times the coincident factor, we got the 2790 watt. And then the maximum current can be calculated by maximum current is the maximum demand divided by the supply 230 volt times the power factor 0.85, we got a 14.28 ampere. And then from this we can calculate the size of MCB. So we know that overcurrent protective device is equal to 1.25 times the FLA. So we got the current is 17.85. So the nearest one is we choose 32M rating MCB single pole. And finally the size of RCD is equal to 32M. So 30 milliampere for power circuit and 100 milliamp for lighting circuit. Okay, now we move to the electrical wiring schematic diagram. So this is the example of electrical wiring schematic diagram. So actually this is the represent your PCB. And then finally this is the flow chart for your wiring installation in a buildings. Okay, that's all for this chapter. See you all next week. Thank you. Assalamualaikum warahmatullahi wabarakatuh.